Dmitri, I'm excited for you to be here on the Silicon Valley podcast. Now, before we start the interview, I know we have a disclaimer. Do you want to start that disclaimer now before we go into anything?
Yeah. Thank you, Sean. It's great to be here. I want to say first, the opinions I'm expressing are my own. I'm not speaking on behalf of the U.S. government or the Department of Energy, just to be clear.
And I also want to say, Axel Cloth, thank you for making the introduction that allows today's episode to take place. And with that, let's go right into the first question. Dmitri, I know your background, did a lot of research, but tell our audience a little bit about your background, your career up until this point.
So, yeah, it depends when you want to start. I'm a product of the Bay Area. I born and raised here, but I found my way through graduate school to becoming a physicist. I was on the faculty at Yale in theoretical physics for little more than a decade and decided to go into government. And I went into the energy department working in the national security side. I worked the nuclear weapons science and technology program for many years, delivering world's fastest supercomputers and technologies with a lot of purpose behind why we did it, which is part of what the reflections are today on here today. I was chief scientist for the National Nuclear Security Administration for about 10 years, became deputy undersecretary for artificial intelligence and technology at DOE for a little while as well. And, here I am now looking back on technologies and thinking about some of the hard problems we face as a society, and how technologies can be brought to bear on that.
So basically you're saying this is going to be an amazing episode.
I hope so.
So with that, with your study, your career, can you talk to us a little bit, from being a faculty at Yale to now, giving advice to the most powerful people in the world? Can we go back to kind of that science revolution? Kind of the history, the step-by-steps from your research, what we should know about.
Yeah, how I think about computing, the context and how I view artificial intelligence today, high-performance computing, and where we are going. I step back and I look to see where have we come from? Why are we where we are today? To give some broad context to where we could be going tomorrow. I think it's a deep question that you ask for a number of reasons. And I roll back the clock a lot to look at this, and I look to the scientific revolution, kind of an important part in kind of human development from the end of the 1500s to start of the 1700s, just over a century in which the knowledge, the discipline of science was developed. What we face today are problems in how do we innovate? How do we do discovery? How do we answer complex questions for the problems we face? A lot of society's issues today, we have to place bets because we can't fix every problem. And so we have to do our best guess on what our hedges are going to be against what could happen that hasn't happened. And you can't do everything. Where do you place your bets? How do you make those decisions? And so I look back to how we did things in the past. Why are we a technology-driven society today? And how can the technology paths we're on today better prepare us for the things that we have to do when the decisions we make have no do-overs? And so there are 5 things that came out of the scientific revolution. That 2 of which I think are important for today. One was the culture of science, how you do that authorship and how you present and prepare and conduct science. Another one was the language of facts. Another one was dissemination of information, the printing press, which allowed people to see things. But there was the discipline of data, people who were invested in instruments, measurements, how you measure and take data. So the whole data apparatus kind of grew out of there. And the last one was theory, how theory developed, the discipline of theory. And And of the things that I look at today, I see that high performance computing, the kind of genesis from the Cold War in the 1940s, post Manhattan Project, and the development of microprocessors and computing, and the work of von Neumann and others that developed the means to solve theory at scales that are unprecedented, beyond pen and paper, and also at the same time, much slower because we couldn't store data, was how we understand creating knowledge from data. And today's AI revolution is really built on how we do that better. The ability to store data, to create novel chips, is putting us in a place where we've accelerated the use of data and the creation of knowledge from data in ways that are, again, beyond human comprehension. And so we've pushed two of the dimensions of the scientific revolution, which was fundamentally transformative to human society. It led to the Industrial Revolution and the technology society we're in today. That was the importance of the scientific revolution. And now we're at a place where we've taken two elements of the scientific revolution, HPC, high-performance computing, the ability to solve theories beyond human comprehension at remarkable scales, and the ability to process data at remarkable scales, again, also beyond human comprehension. And we've pushed those to places that are just staggering. But innovation and the seeds of a lot of the problems we have to solve today live in between those. And that's what I worry about, to know everything that could be, as well as things that have been. And bridging those is where discovery and I think complex decisions are going, and the technology paths are going in different directions. And so I look at where we've come from to give context to where we are today and a sense of what could be the next fundamentally transformative thing on where we should be going tomorrow.
Oh, there's a lot there.
Sorry about that. You should just cut me off if I ramble a little too much about this.
No, I loved everything. I'm really interested in that part in between where they're divergent. But I also, even before we get there, with the history of science and looking back to kind of predict the future, what should entrepreneurs take away from this science revolution? What lessons, knowledge can they look at, can they learn, and can they, grasp and maybe potentially help them or implement in what they want to do?
It depends, a great question. And I think if anyone had the right answer to that, that would be a wonderful thing. I will give you my perspective on some of this. What do you take away this? Where are we headed? Why are we headed in certain directions, and what's missing? I think to disentangle this a bit, there are, you have to keep in mind that discovery and invention are different things. There are areas where science leads technology, where discovery leads invention, and there are places where invention leads the science. And so they don't necessarily work in lockstep. When I look at AI today, machine learning broadly, and to some extent AI with all the technologies tied to data ingestion, aggregation, and decision making, and so on, it is a technology, in my point of view, without a science. If you take quantum technologies, which is a place where investors have been putting money, which is a long game, I would say, quantum technologies today are based on quantum mechanics, which was developed almost 100 years ago in the 1920s. And so that's a place where science has led technology. And so there are, the reason I say that AI or machine learning is a place, a technology without a science, is because we don't understand the fundamentals of why things are, or we wouldn't be asking about transparency or or ethics or bias or things. There is no fundamental technical or scientific construct that bounds the box in which we understand the field. And so there is no set of axioms or principles that we can build the theory of machine learning on that can answer the questions. And a lot of it is really engineering exploration. People are tweaking things, creating new methods, new technologies, new ideas based on tinkering. It's a technology game. And so, going back to your question, what should people be looking at? If you're playing the short game, today it's about commercialization and markets, right? Who could use this or that? It's kind of a doing small steps in creating value to people that they might find useful. I would say the long game, in the same way people look at fusion today, which is a place with a fair amount of venture capital as well as quantum technologies broadly. The long game, I think, is in this intersection of computing and AI, the data side and the theory side, and how you bring those worlds together. That, I think, is an interesting place to go.
For society to be at this place where they're open the technology and everything coming together, how did culture in this time have to evolve to be at the place where they're open to both these ideas, both these sides coming together?
It's a unique moment in time. I think you can. So I grew up here again in the Bay Area at the time when companies were growing. Hewlett Packard and Intel, and kind of the fundamental staples of technologies that created this valley. And you couldn't really see it at the time. You could kind of feel it, but people write books about it now. And at the time, because it was just the way the world was, you kind of took it for granted that these things were happening. I think we're in a moment like that today. We kind of take it for granted, but the pace of investment in new technologies, in AI chips, in altogether brand new things is remarkable today. And it's not natural. It wasn't happening 10 years ago, and certainly not 30 years ago. We had a small revolution in computers in the early 90s. I had a friend that collected the mugs of failed computing companies, and he had a whole window full, stack full of these things, which were, reflected a remarkable time of innovation in this country. And we're in another one right now. And I think we are lucky to be in it. And I think it is rare. And we should be thinking about what this means. Why are we in this time? Because we're lucky. What should we be doing? Everything we can. People are looking for ideas. They're innovating in ways, but everyone's kind of looking for what is next, what is going to happen. And because of that, there's remarkable opportunity that you normally don't have. In every sector of the economy, people are looking, can I do something here? And it all distills back down to these kinds of technologies we're looking at today. And so it's a remarkable time. And I think we should all be happy to be here right now. And there's probably always more we could do.
Very early on in the interview, it was mentioned making decisions that, big decisions you can't go back from. How does one go about making complex decisions? What is that process?
So, that's a great question. A lot of the decisions that we make today, where you draw science in on, are based on simulation, on computer simulation. And that's the world that I was in for many years. Using supercomputers to solve problems that are really sparse in data. So you don't have too much information on them. You are trying to solve questions. For example, I was in the nuclear security world. What could happen? What bad could happen here? Which is a very broad question. You do your best to simulate things, but the scale of problem is 15 orders of magnitude in length, typically from the scale of the nucleus up to the scale of us, scale of weapons. Or if you want to know what happens within kilometers, then on kilometer scales, it's more length scales. And so you think about 15 orders of magnitude, and that's like trying to manage the federal budget, which is measured in trillions of dollars at the tenth of a penny level. It's that kind of granularity, and so we create models, numerical models that work at scales from the nuclear scale to the atomic scale to the micro scale, to up to the physical scale of people and buildings. And you have all of that science in one place, and you have to say, well, okay, that much science, how do I trust it? And you create methodologies to try and test them at all the different scales. But you can't actually test what you're interested in because you hope that will never happen. So there is no data on the actual thing you are worried about. And so you create models, you get as much information as you can that is peripheral, you test things as best you can, and you try and bracket the uncertainty. You quantify the uncertainty as best you can to provide guidance to decisions that will be made. The decisions typically live outside of the mathematics and the models. And so you have to at least try and bracket the confidence that I'm certain this is going to fail, or this is likely going to work with 85% confidence. But it's not a simple mathematical process to do so. Simulation codes can be millions or tens of millions of lines of code. Given that a single person might know where 50,000 lines of code might be or what it means, it is necessarily a compendium of experts working together in very complex ways to provide the confidence you have at the end of the day to help with these decisions. So it's non-trivial. We spend billions of dollars every year working these problems. It's like painting the Golden Gate Bridge. Once you get to one end, you go back and you start again. And so there is a cycle of work that is continuous as we update models and codes, do better experiments to help make the decisions we need.
These simulations, how creative, how broad can they actually span? I mean, where does that boundary of we can't creatively think of anything more to simulate for this? Where is that?
The biggest problems of models is not knowing what you're missing. And you try and test them experimentally as close as you can. The challenge with the nuclear security, the nuclear weapon side, is you have to simulate things that are similar to the temperatures and pressures at the center of the sun. And so you can't reproduce that in the laboratory. And so your question is right. You can't simply run a single model or a single set of models and say, here's my prediction. You have uncertainties that aggregate in funny ways, not simply in quadrature. They don't add together in nice ways. They can be based on the mathematics you use to solve your equations. It could be based on particular choices of materials or particular favorite equations to simulate different kinds of materials or flows. Or there are many ways that uncertainty can creep into your models that have to be captured, and they're always the things that you miss. You hope that you can bracket that with a few key experiments, but you have to be aware that you probably won't. And so given that you're going to miss things, how many different ways do you want to do it so that you at least have a sense, well, I probably have boxed it in. And if all of these are in fairly good agreement, then I have a fairly good sense that this is the answer. But it's not take looking up at the sky. For 1,500 years, the favorite model of the solar system was due to Ptolemy. from 150 AD. It was called Ptolemaic epicycles. And so you could model the motion of the planets with circles in circles in circles, and all these nested circles, because circles were the preferred shape. And you could even look at the sky and model retrograde motion of planets like Mars, when it kind of goes forward in the sky and then goes back and then moves again. So you could have a detailed model, and it was wrong. Eventually in the 1600s, during the scientific revolution, Newton, the models of gravity and Kepler and so on, created a better model. But for 1,500 years, the wrong model stood, and people believed it. And so you can believe for a long amount of time that what you're doing is correct, but it likely isn't. And so if you had taken the Ptolemaic model and said, I wanted to launch a probe to land on Mars, it would never work. You could explain exactly where Mars is in the sky, and if you knew the distance, you could push a probe and send it in that way, but it had no gravity in the model. So as soon as you launched it, it'd be pulled toward the sun, and it would never get there, even though you know exactly where everything is. So the lacking science within the model, which was not visible for a millennium and a half, there are a lot of problems that were outside of that model's capability, and we always struggle with that. The science we do today is always incomplete, and you have to understand that whatever you predict is incomplete and wrong in some way. And so, how do you bracket the wrongness in making a decision? And that's a bit of a science and a bit of an art.
With that, then, I mean, the model, how important, because you'll hear, bad data and bad data. How important is having that data? How important also is having, high performance or the most up-to-date, most powerful computers working on these models?
So it's been important. So the world we came out of was solving math equations. And that came out, again, of the Manhattan Project and the Cold War. We developed and built computers to solve a lot of these equations. And so I delivered a lot of these state-of-the-art systems. We were talking in the early 2000s about running on, in 2003, we were talking about running on 1 million processors. People thought that we were stupid. But as we looked at, literally kind of laugh you out of the room, don't talk about that. We did eventually deliver our system, the Sequoia system, in 2012, which had 1.5 million processors. But in 2002 and 2003, people thought scaling to 1 million was just not going to work. We looked at the scale of problem that we had to solve from the point of view of mathematics, and said, this is where we have to go. We needed at least petascale, petaflop performance. We needed exaflop performance. How do we get there? And there were several paths that I was involved with, that I was responsible for. One was going to massively parallel architectures. Again, million-plus processing. We started with the Blue Gene series. We pushed to 100,000, and then 250,000, and then eventually millions. And then it became natural for everyone to do that. But I got to tell you, when I started in this, it was really ridiculed as the law of large numbers would kill you. Something would fail. You'd never get any kind of coherency or consistent simulation across this. Another way was recognizing the bandwidth to latency problem on these systems. We crunch a lot of numbers. The massively parallel systems had very low memory per processor, per processing element then as well. And so our bandwidth problems, our latency issues were eating us up. And so we developed a network interconnect chip back in the early, again, mid-2000s, which was called the C-Star chip. Eventually, it was what transformed Cray from a vector company to a massively parallel system, and it led to their XT3 and their XT series of supercomputers that transformed their business and kept them viable till they were eaten by HPE. And the third path was heterogeneous architectures. So we started again in early 2000 in trying to understand what we could do with graphics processors and how we could create a heterogeneous architecture. At the time, DARPA was pushing for a petaflop system. They had a 10-year grand challenge, 2001 to 2010, DARPA HPCS. We delivered a petaflop in the end of 2007, early 2008, using graphics processing, using the PlayStation 3 chip. It was the first petaflop system. Unfortunately, we didn't have enough data to do the kind of machine learning you could do today, because you just couldn't archive big data at that time. But I would say this was a kind of problem we were looking at. And so we had these accelerated systems there too, as well. And the Roadrunner system at Los Alamos was novel at the time, but today these are kind of, yeah, of course you do that. But at the time, I would say it was hard to create communities of practice around heterogeneous architectures like that.
Can you talk a little bit about how difficult it must have been to say to people, yeah, this is possible, we can build this, it'll take years and years to do it, but it is possible, with probably in these communications, half the people you're talking to not understanding a single thing you're saying?
I think it's hard. You know, it's not that you want to create these, it's just that the problems you're trying to answer are hard and they make a difference. Nuclear weapons are an interesting world because the problems are real. You have 18 to 20-year-olds that move them around every day. We drive them coast to coast in this country, and we've driven more than 100 million miles without incident from Washington State to Florida, from Texas to North Dakota, coast to coast. We drive these things around. We pull them apart. We have a site in Amarillo, Texas. You open them up, and so here's the situation. You take one of these things that hasn't been, it's been in the field, moved around by youngsters for decades. They're decades old, and you take some and you crack them open. And it's not like watching Peacemaker with George Clooney and Nicole Kidman, where you take the butt of a gun and a pocket knife and you open up. There are big, complex tooling sets to open these things up. And you open them up and you look inside and you say, this is corroded or this is cracked. Does it make a difference? Do you keep all of them in service? Or what do you do? Is this a safety issue? Is it a security or performance issue? You can't test it. And they're in the field. So, and this is the kind of question, a class of question you end up with. How do you answer that? Well, we look at the science that we need to address it, and we create the facilities. We push the computing. We say, this is going to be hard. It's going to take this level of computing. Well, we can't do it on these architectures. And we had the number one system during my tenure there for years. The world's fastest system were the systems that we were delivering. And it wasn't just for show, because, in Washington, these things are ephemeral. You don't care. It's someone's press release, but for you, it's how do you answer these questions? Is this a problem? Because behind a decision like that are safety and security issues for the country, for people. It is billion-dollar investments if there are real problems. And so you can't just say, let's be conservative and say this. No, you have to know how to answer these questions with the best of what you can do. And it has stressed the computing over the years. And so we have pushed the limits of high-performance computing for that reason, because we didn't have the data. You can't test it, but we have the models. And so the frontier of computing was a place we lived at as just the course of business to answer the questions that we are faced with.
I mean, being prepped to answer those questions at all levels, how is technology how is technology at every level of the government being implemented to have answers, to prepare for questions I mean, we see stuff on TV. It seems like people are just giving speeches, just on how they feel, but there's so much more going on in the background that none of us know about. How is it at each level? How are these models being implemented in preparing?
I think it's uneven. It's uneven because it's where the country has chosen to place its bets. What are the ones that we really have to understand today? And so it's a mortgage to be in the business. The systems are expensive. The teams that you need, the people are unique skills, and so it's you can't do it everywhere. But a lot of the capabilities you create to understand these problems are transferable to others. So they're not just standalone. But if you know how to do and program on these, complex heterogeneous architectures, if you know how to work the discipline of answering questions or making decisions, then you can translate that to other places. But no, it's not done everywhere at the same level.
And high performance computing. Why make it? Why is it the future? How much impactful is that going to be?
Well, so here's a challenge I see that if you read the early papers again of von Neumann among others, not the unique person to read, but just one I have enjoyed reading. He laid out early on back in the mid 40s the memory architectures and hierarchies and microkernels and interconnects, and he kind of laid out the designs of systems which were based on solving mathematics equations. And that's the world that we lived in for a long time. What we could do with computing was solve equations. So you didn't have a lot of resident data. You didn't have petabytes or exabytes of data sitting around that you also needed to process. You created numerical data from your simulations, and some you stored and some you didn't because you couldn't afford to keep it all. And so there was one world based on making predictions from models that excelled. And now we're sitting in a world where we can create sensors, we can create detectors, we can store data at remarkable scales with remarkable granularity. You can do really complicated experiments and store time, evolution of complicated things, well instrumented. And people apply machine learning to these kinds of systems, but we don't have a place for that world to interact with the simulation world. Those two go independently. So we can augment high-performance computing with accelerators. We can do interesting things there, but we can't take rich data environments and embed them into simulation. So why is that important? Well, I don't believe you can learn everything you need from data. Data tells you where you are today. It gives you a limited view of the world through a particular lens from which you can learn some things. A lot of things we care about aren't in the data. If you're worried about rare events, if you're worried about society level problems, if you can make decisions, but if you get it wrong, there's no do-over. You have to be able to simulate things. You have to be able to run the clock forward 100 years or back 1,000 years. You have to create scenarios that are not real world, but could be. And you have to say, how does that intersect where we are today? How do you get the world of data, everything you can measure, together with all possible futures, and use that to make a decision? I don't know. That's the technology gap I worry about. It goes back to your entrepreneur question. What are the things I worry about? It's this gap between pushing simulation as far as you can and pushing the machine learning part, the neural network part, the knowledge from data side, but trying to figure out how do those worlds connect. In the scientific revolution, in that period, you would have unique people that saw both worlds. They understood all the theory, they saw all the data, and within their mind, they could come up with those, epiphanies that those singular contributions that propelled society forward. Now we're in a place where no one quite understands the simulation side, the theory side, and no one really understands the data side, but the place you have to be is in between. And we have no technology that allows you to get those two to work together.
By not having any technology that lets those two work together, are there any problems that we're going to see in the future because of that?
Well, you want to know, every day we all want to know, well, what decision should I make today that will impact me? What are the potential futures that make a decision today based on the information I can gather will optimize the path that I would like to be on? That is a blending of prediction with data. Where you are, everything you know, as much as you can about today's environment, but all the predictors you can get from the best models of where we've come from and what could happen, things that aren't measurable. And blending those together is a more interesting place to be than just looking at resident data and saying, this is what we have. It's retrospective. If you want to look forward, you're going to need more. You have to bridge the two worlds of HPC, the simulation, the theory side, and the data side.
How do you think our lives are going to change in the future with artificial intelligence? Like from an actual, that's such a broad answer, I know. And I know that one question could be for an entire day, but I guess try to narrow it down a little.
I think it'll become, it simply will be accepted that this is what you need every day to get by. I look at my grandson who interacts with Google, all by himself, talks to it, pulls down content. He looks in the car and he sees a speaker. It says, "Is that Google? Can he talk to it?" There will be expectations that everything is smart, that everything is aware in some way, pulling information and relaying and informing you, and it'll become routine for us. How will it change us? I don't know. We will expect it to be there day to day to make our lives easier in some way. So I don't know if it will transform us, but I think we will evolve into a place where the world around us and its impacts on us are more aware to us on the things that we do, and it'll just be expected.
What do you think then is next for computing?
Computing, the easiest path for computing is faster, because we know how to do that, and we've been doing that for years. I think the hard path is how do you blend it with rich data? If I'm creating an exabyte of simulation data from my models, and I've got exabytes of measured data, and I want to say, well, how do these work together? What does this mean? We don't have a way of doing that. So we could do faster. Faster isn't enough, from my point of view, for either scientific discovery or for complex decisions. To make complex decisions, we need to know everything that we can about where we are in the world, everything that's going on that's relevant to the decision. And we have to have all the sense of what the future inevitabilities could be and what the downstream impacts are of decisions with as much understanding as possible. And those are two separate worlds right now. We have the AI chips and the AI accelerated systems that can do remarkable graph solutions of problems that will help us in remarkable ways, which is great, by the way. But I don't worry about that because it's going and it's going to happen. It's happening right now, and it doesn't need our help. And we'll have faster supercomputers. But what we need is the fabric that connects these two worlds. And we don't have that. We don't have the interconnects. We don't have the ways for these to talk together. And we don't even have the scientific concept of how you could evolve a simulation in the cloud of everything you know to see if you could bracket the confidence in any outcome that you want to make a prediction on. We can't do that. I'd like to do that. I'd like to say this is what I think will happen based on all these measurements and all our models. But usually it comes down to a person taking a few main key points of data, maybe from a spreadsheet, and creating a 2D plot with a line that says a prediction and experiment, or something similar to that is digestible. But you throw out the full richness of everything you can measure and everything that you've simulated, with the hope that what you're looking at is the right metric for saying, yeah, this is a pretty good prediction. I would say we could do far better, but we don't have a way for these two worlds to talk to each other technology-wise, and they're just moving farther apart.
I was going to ask, do you think in the next couple of years they'll start coming together, or just for the next 10, 15?
If we're deliberate, they're not going to come together unless people work it. But I think not everyone lives in this space. If you look at what's happening in AI, I saw last year the Credit Suisse estimate of $40 trillion market. It is driven by near-term commercialization, and I get it. Of course, it should be, but people are making architectural decisions right now on these technologies for some of this near-term gain. Are they the same kind of decisions you would make if you take a longer view of what's beyond AI? And there is a world beyond AI. AI, machine learning today is great. AI is great today. But if we found a different way to do the same thing, what we care about is the endpoint. We don't care about the AI. And I look at it, I talked at the beginning when we were first started to chat about technology and science and technology leading science, or science leading technology, and that machine learning and AI today is a bit of technology leading the scientific understanding of what's really there. What are the limits of what you can do? How do you box it in? We don't know. And so, we stress it as much as we can, but we don't know exactly where the technologies are going to take us. And so, yeah, I think I've lost the train there on as I was thinking about. So what I was going to say is, as I think about AI today and machine learning, what's next there? I think of the steam engine. Steam engine. People understood steam in the late 1600s, steam pipes. People didn't understand why the steam engine worked. And the theory of the steam engine didn't happen until 1824. And so for more than 100 years, people tinkered with it. And they found out in many cases the hard way that this technology had its limits. Steam engines exploded. They tried different things. There were all kinds of models. The steam engine was transformative for the Industrial Revolution. It was not the end point. The goal was not the steam engine. It was kind of the industrial society, the tooling, the creating the industrial side of our society, and the steam engine kind of evolved from design to design, hit or miss. We tinkered with it and eventually ended up in a place where we understood how good it could be, the final efficiencies, what's the best design you could make. But that came a century later. I look at machine learning, AI in this world today like the steam engine. We tinker with it, we push it, we get things better. We don't know exactly why. What are the bounds of how good it would be or where it could go? We have no idea because there's no theoretical context for what we're doing. So what's it going to do? Where's it going to go? I don't know. It's going to be hit or miss, trial and error. As we engineer our way forward, there'll be a lot of interesting innovations. But I think without any founding theory, I don't know exactly where it's going to end up. But in the end, it might not matter. Like the steam engine, it was eventually replaced by other things. Steam engine is not the center of our world today. It's more of a curiosity, or, we find it still in some places. AI might very well end up in the same place as we develop further and we solve our problems and the things that are important to us in different ways. it might end up being also like the steam engine, significant, important, transformational over time, but not the end point. And so I go back to the place in your initial question on entrepreneurs and so on. Ask yourself, what is beyond that? Beyond tweaking things and making things 5% better here or 10% better there or this or that. In the big picture, what is beyond that? Where are we headed? Why are we headed? There's a lot we can learn from how we got to where we are today to think about the landscape in the future and where AI will find its place. I have a sense that there are bigger things out there that it will help us get to, but it's not an endpoint. And there are other things we should be reflecting on beyond the $40 trillion market that is driving kind of let's develop this and that and the near-term stuff. I think we need some component of people taking the long view of, okay, what is more transformative to society? Where are we going next? How do we get ahead of this? I think we have nothing but problems that we face, what we don't know the answers to, that vex us all, and that there are opportunities to ask ourselves, can we do something better to help those? And I think AI will be a part of it. I think computing will be a part of it, but there is a missing piece as well that we should be focused on to get us beyond all of this.
Moving forward, the idea of the advancements of technology, how important will technology, being the pioneer, being number one, be for maybe a country's position in the world? I mean, there's natural resources, there's currency, how will technology be number one? How important will that be moving forward?
I think it's key. It's really important. What I like about the Bay Area, what I like about the way innovation is done here in the U.S. is its openness, the ability for anyone to start a company with relative ease, with a few people, the richness of venture capitalists who are willing to take a lot more risk today than perhaps in the past, and I think there's a lot of opportunity that we should further try to enable to help nurture this along, because again, it's a unique moment in time where everyone is focused on this, from those that provide resources to those that have ideas that are looking for them, and we can't squander that. So I think this is important to try and push as much as we can.
How different is it from teaching a lecture versus kind of informing the government?
That's a great question. Having come out of academia, I wasn't sure if I would like government, but it was something I felt kind of a calling to try and provide some value from for the things that I've learned, and my sense is that they're inversely related. So life in academia, the whole universe was your field. By definition, you're working on the most interesting thing. The whole purpose that, we create, we write papers, we do our work. The point is to get citations. It's to go to conferences and tell everybody about your excellent ideas, why they should be paying attention to your work. And it revolves around presenting the intellectual content of your contribution in a way that others will recognize. And so that is that kind of world. In government, it's 1 over X. It is inverse. You write white papers, authorless papers on positions, and if you have good ideas, the only way they get any traction is you have to get many, many other people to feel it is theirs too. If it can't be yours. If you write a paper and say, this is my idea, support it, no one cares. You need people in leadership roles at the most senior levels of government to stand behind it, to cash in political capital, to say, this is important to do. They have to own it or nothing happens. And so you push ideas, you get people to support them. You are not recognized as the author behind those, because you don't want that, because that kind of poisons things. You want everyone to feel like it is their idea. And when you get to that point, when people meet you and tell you about the interesting thing that they're going to do, and it's where it came from, that's exactly where you need to be. And so it is the opposite world of trying to mark your success by how recognized you are in terms of your personal contribution, your citations, and your work. You have to be satisfied that the outcomes you've achieved, that you've helped move the ball forward on, make a difference. And if you're personally happy with that, which isn't for everybody, it's a good place to be. And it's important to get people to do that. We need good people doing these kinds of things, but you have to separate it from yourself. It can't be tied to your sense of self-worth in the same way that it is kind of in academia.
I'm just picturing someone coming to you asking for your opinion, and knowing that you are the one that wrote that.
Yeah, it tells you it's getting traction. It could happen. So big transformative things need something like that. The ideas come from somewhere, but you have to have a groundswell. And writing a single paper and publishing it somewhere is not the mechanism to do that. It is working, all the different elements of who you'll need to make something come to fruition, and getting them to understand it and repeat it, and feel that it's important enough for them to spend their time on it. And then it becomes theirs. And then you can do heavy lifts. Then remarkable things can happen.
And one thing is, we are the Silicon Valley podcast. A lot of our listeners are entrepreneurs, venture capitalists, leaders in tech here in the Valley. A lot of them want to have access to Washington. Any tips or tricks for them to get, in contact with people over there?
I think it's Washington can seem like a mystery to people. How do you interact with people? In the end, you sit in offices there, and you don't have a lot of time. A lot of the goal is to get things off your desk, as fast as possible. Let's move this along. Otherwise, things simply accumulate. But there is always time to meet with people. When I've been there, I've always kept an open door policy. Stop by. I encourage people, faculty, companies, whoever. Just, you have an idea, stop by, but please be able to convey your idea quickly if needed. Because an hour meeting can be a 5-minute meeting in the end, because schedules get jammed up pretty often, and so it can't be excruciating detail. What's the bottom line? What's important here that should be on our radar, and then you can dig in more. You have to have the bottom line out front. You have to understand why this is important, but people don't use it enough. There isn't a visible Washington presence of a lot of small companies, and people don't just fly there and talk, but you should. Doors are typically open. Pick an agency, cold call them and say, hey, I'd like to come out and tell you about this. And things can happen, but it's really up to people to be, to lean into this.
Dmitri, this has been an amazing interview. We're now at the top of the hour. If anyone wants to find out more about what you're working on, what's the best way to go about doing it?
Well, that's a good question. What I'm working on isn't always visible, but I think that's a hard question in general. In terms of what are people working on in government, especially, you don't always share what you're working on, but I think if it comes to technologies broadly, there is always an appetite for new ideas and talking with people and seeing where the innovation is. And you don't have to be, chair professor of X or CEO of Y to come down and talk with people. The door is open at many levels to engage, and you can learn about what's important to agencies in that way. You can read the websites. You can see broadly. The specifics can change day to day, and sometimes just walking the halls periodically, creating your list of people that you come and visit quarterly or at least every year. can be a mechanism to answer that question, because we don't always post online, this is what we're working on.
I was hoping you were going to give out a Twitter handle there or something.
I don't use that for many reasons.
All right, Dmitri, with that, I want to thank you for your time today on the Silicon Valley podcast. I want to thank Axel Cloth for making the introduction that allowed today's interview to happen. For all the listeners, while you're listening to this podcast, please give us a review on iTunes or any of the other podcast platforms that you're listening to this on. It encourages us to create more great content just like this. And for our listeners out there, if you're looking for a mid-market investment banker, please connect with me on LinkedIn. I focus on mergers, acquisitions, growth capital, and secondaries. I'm here in Silicon Valley, and after all the episodes you've listened, I think you know me pretty well. And with that, Dmitri, I want to thank you one more time today for taking the time out of your busy schedule to be here on the Silicon Valley podcast.
Thank you, Sean. Appreciate it.